Let's take a look at exponential functions now. An exponential function is a function that's given in this form. So this is the general form of the exponential functions for us. This f of x is equal to c times a to the x. Now the restrictions, we have looks like quite a few restrictions on each of those components of the exponential function. First of all, a has to be positive. That's the base of the exponential function. The reason the base has to be positive is because if a is less than 0, then many values of x must be excluded from the domain. So for instance, let's say a is -2. So I'm not allowed to do that. But let's say I have -2. The exponent x is any real number here, right? So I'm going to choose x to be 1/2. Well, I can rewrite this as a square root of -2, and the square root of -2, remember, that's not real, because a number times itself, a real number times itself, cannot be -2. So for that reason, we're going to end up excluding an infinite number of values. So for that reason, we just say that the base has to be positive. Now base cannot be 1. Well, what happens if it's 1? That means 1 to the x. 1 to any power is 1. And we actually have a constant function, not exponential. So that's the reason for those two. And c, the constant, cannot be 0, because if it's 0 times anything, you get 0. So you don't have a function to work with. You have just the x-axis, f of x equals 0. Again, a constant function. So it's for these reasons that we have those restrictions. Now, let's see what the graph of these functions is going to look like. So in my examples, I'm going to actually go to my graphing utility and do the graph of these functions. And for simplicity, we're just going to choose base to be whole numbers, okay, or natural numbers, 2, 3, 4. And then we're going to look at a few. Let's say we're going to look at 1/2 to the x, 1/2 to the x. Then we're going to look at 1/3 to the x, and we're going to look at 1/4 to the x. Okay, so let me do that. Let me bring up my graphing utility, and we talk about the behavior of the graph of these exponential functions. And here we are. Now clearly you can see I'm doing this in Desmos. If you never use Desmos, try to really explore the possibilities with Desmos. It is like a graphing utility, and it does so much more than just graph functions. So I highly recommend using this utility. The website is desmos.com. And it's free. Everything you do there is free. There's no charge for it. Okay, now to the left you can see I have those functions that I mentioned about. Let's start with 2 to the x. So I'm going to activate my graph of 2 to the x, and there it is. So here's a graph of that function. I'm just going to shrink it a little bit. You see how that goes? The exponential growth portion of it is actually as y goes from 0 to infinity. You see the sharp ascend of this function. Now for negative values, you can see the graph approaches the x-axis. And although it looks like the graph is touching, it's actually on the x-axis, but it's not. The graph is asymptotic to the x-axis. In other words, there's a horizontal asymptote, which is the y-axis. I'll explain these in a few minutes when I go back to my note. So here's a graph of 2 to the x. Now we can make some observations here. The y-intercept here is at 0, 1, right in here is 0, 1. The function is rising. That means it's increasing as you go on the x-axis from left to right. The function actually rises. Now let's take a look at overlaid on top of this in the same coordinate system. Let's do 3 to the x. So the graph in blue is now 3 to the x. So with 3 to the x, what happens, as you can see, 3 to the x takes over 2 to the x beyond 0. when x is past 0, 3 to the x is larger, right? As the base grows, so does the y value. Now, something interesting that happens actually is before 0 on the negative side of number line, you can see the blue curve lies below the red. So for negative values of x, 3 to the x is actually smaller than 2 to the x. Both functions go through 0, 1, which is the y-intercept of the graph. Now let's do one last one, 4 to the x. And check this out. Again, 4 to the x beyond 1 surpasses 3 to the x and 2 to the x. But for negative numbers, it's actually going to be lower, smaller than both of those for the same value of x, but negative. So we're going to make this as our general observation. Okay. Now, let's take a look at, I'm going to remove, inactivate these. Let's take a look at 1/2 to the x. So here's a graph of 1/2 to the x. Remember what 2 to the x looked like? This one? Check that out. 1/2 to the x is actually the mirror image of 2 to the x. Because 1/2 to the x, we can write it. Remember, 1/2 is 2 to negative 1 power. And 1/2 to the x would be the same as 2 to negative x power. And 2 to negative x versus 2 to the x, there will be the changing of x to negative x here causes a reflection about the y-axis. Okay, now look at 1/3 to the x and look at 1/4 to the x. So this time, because you have a fraction, as x gets bigger, the fraction gets actually smaller, right? So there you go. Here's your 1/2 and look at 1/4. See, the x value is actually smaller for positive x's. And for the negative values, it does just the opposite. So you're looking at, for instance, again, this is 1/2 to the x. Look at 1/3. For negative values, it actually lies above. 1/3 to the x lies above 1/2 to the x, and 1/4 to the x is going to lie above both of those for negative values of x. And there you go. All right, and then I can now kind of throw these together. Let me go. This is the graph of 1/2 to the x again on the left, 2 to the x on the right, which is the red. The red is 2 to the x, the blue is 1/2 to the x. Let me change that to 3 to the x versus 1/3 to the x. See, those are mirror images of each other. All of these go through the basic point 0, 1, and they all have horizontal asymptote, which is the x-axis, line y equals 0. Let's look at 4 to the x versus 1/4 to the x. Again, perfect symmetry. You're looking at perfect symmetry here. See that? For the graph of this function. All right, so now we're going to generalize this in my note. So let's go back to my note now. All right, so we are back. Now let's actually take a look at the general graphs of 2, 3, and 4 to the x. In general, if the base of the exponential function is greater than 1, such as 2, 3, 4, and remember, it doesn't have to be whole numbers 2, 3, 4. It could be 2.78 to the x, it could be 3.14 to the x, and so on and so forth. For simplicity, I'm looking at whole numbers here, or natural numbers. So here's what the graph's going to look like. In general, the graph's going to be rising as you go from left to right. The y-intercept is going to be at 0, 1. And there you have it. The exponential function will have a horizontal asymptote, right? Let's actually write the relevant information here. One thing also you can note about this function is that it is 1-to-1. It passes the horizontal line test. So the function is 1-to-1. An implication of that is that the inverse exists. And we will be interested in the graph of the inverse, by the way. But we'll do that in the next section. The function is always increasing in this form, in its basic form, increasing. over the entire domain negative infinity to infinity. Okay, what about the xy intercepts? We already mentioned the y-intercept is at 0, 1. X-intercept, the graph does not have an x-intercept, so we're going to say none for this one. Again, the horizontal axis is going to be the x-axis. The horizontal line is going to be the asymptote of the graph, and in this case, the exponential function doesn't cross nor touch it. And the reason is this. Remember, this is y. If we set y equal to 0 to find the x-intercept, because y is 0, we try to solve 2 to the x equals 0, and then you begin to think, well, what makes 2 to the x 0? If you're thinking 0, well, 2 to 0 is 1, not 0. Remember, any non-zero to 0 power is 1. And if you go with positive numbers, 2 squared, 2 cubed, 2 fourth, well, none of those become 0. If you think of 2 to negative 1, for example, that's 1/2. See that? Which is not 0. So there's no way the basic exponential function without any transformations can be 0. So for that reason, the graph of it is not going to cross the horizontal asymptote. It will approach the x asymptotically. And since I mentioned the horizontal asymptote is going to be y equals 0, namely the x-axis. All right. What about the domain and range? Should have probably started with those first, but that's okay as long as we cover all of them. The domain of the exponential function is going to be any real numbers. You can plug in any x value. See, it projects, any x projects to a y, so x can be anything. And when x can be anything, we write it as negative infinity to infinity. The y values are along the y-axis, right? So because there is no graph below the x-axis, y has to be above 0. Not including 0, because if it's 0 means it's touching the x-axis, and we just said it cannot do that. So it's going to go from 0 to infinity. All right. And so those are the key highlights of the exponential function, those 7 things. And that is if the base is greater than 1. What if the base is actually less than 1? So for instance, let's say this is what the exponential function looks like now. And remember, for those, we looked at the graphs of 1/2, 1/3, 1/4, and so on. In general, this is what the graph would look like. So again, the graph's going to go through 0.01, and this time it's going to be still 1 to 1, so its inverse exists. The function is this time sliding, decreasing as you go from left to right on the number line. See, the graph is going like that, so it's decreasing without crossing nor touching the x-axis. Your y-intercept is intact, still 0, 1. And let's see, the x-intercept, we said this one would be none, right? None. The horizontal asymptote will be exactly the same, y equals 0, the x-axis. Your range and domain will also be unchanged, domain all real numbers, and the range is going to be 0 to infinity. All right, so we have those, and this is good for a between 0 and 1. And remember, it cannot be 0. True, it cannot be 0. If a is 0, base is 0, by the way. If a is 0, you get 0 to the x, which is 0. So for that reason, a cannot be 0. Cannot be 1 because we said it's going to be a constant function, and so between 0 and 1, this is the behavior of the function. All right. Now, sometimes we are interested in solving exponential equations, so we'll look at that in just a moment. But before we do that, let's take a look at some graphs of these exponential functions, and we're going to use transformation of the basic graph to graph these. And let's say I'm going to make up some problems. Graph f of x, and for this work we're going to report again the domain, range of the function, and let's do the horizontal asymptote, and let's do the y-intercept. These are all going to be exponential functions, so it's going to be a variation of the ones that we saw earlier. So for example, let's say the function, we're going to make it 2 to the x. We already saw the graph of that, right? Let's add one. Okay, so here it is. I went ahead and graphed this for you. And we're going to look at all of those key values on the graph of the function. So let's begin with, first of all, the graph. So I started with the graph of 2 to the x. That's the dotted one. Okay, that's this one. And then we move this graph up 1 unit. So the red is actually the graph of f of x that we want. The horizontal asymptote was the line y equals 0, namely the x-axis, and that floor, or the horizontal asymptote, also lifts up 1 unit. Now it's at a height of y equal 1. The y-intercept used to be at 0, 1, moves up 1 unit, so y-intercept is now at 0, 2. Talked about horizontal asymptote. The domain is unchanged, and the range now starts from the higher floor, 1, not including 1, and goes all the way to infinity. Okay, now let's take a look at this one. This next one, we want to graph f of x 3 to the x minus 1. So I went ahead and on the right side here, if I let my basic exponential function be f of x equal 3 to the x, next to that, then f at x minus h is going to make that 3 to the x minus h. So that would mean that x minus h here match this x minus 1 against x minus h. So you can see that h is 1, h is positive, so the shift would be to the right. Again, the dotted curve is this one, is going to be the basic one, that's 3 to the x. The one on the right is actually f of x that we are seeking. Okay, so that's what that one is. All right. And the point that was 0, 1 moves to the right. There you go. Everything indeed shifts to the right. 1 unit, including that 0, 1 is now at 1, 1. And these are some of the basics that we can observe from the graph. Domain is unchanged. The range is unchanged for the basic, 0, because there's no vertical shift. So the range is unchanged. And the y-intercept, you let x to be 0, which is what I did here, and got the y-intercept to be at 0 and 1/3. All right, entirely using transformations. Let's take a look at this one. Now for this one, 3 to negative x. So I'm thinking the basic function 3 to the x, and if this time I'm thinking about the transformation that we talked about, the transformation of the function. This is g of x, g of a of x, where a is negative 1, right? A is negative 1. Now, if you go back again to our earlier discussions, earlier lectures, g of x, change it to negative x. We get a reflection of the basic function with about the y-axis. This is the y-axis. And there you have it. All the specifics. Now the y-intercept doesn't change when you do a reflection about the y-axis. And neither do domain and range. X-intercept still none. The horizontal asymptote intact at h equal at y equals 0. Now, if I drop that, by the way, down 2 units, the same function, this one, if I do minus 1, I simply drop the basic function that we just graphed, that red curve, we drop it 2 units. And that's going to affect the y and the x-intercept now, right? So the y-intercept, that's when x is 0, turns out to be at negative 1. And so what we used to be at 1 drops 2 units, now it's at negative 1. Okay, and this doesn't mean the x is negative 1, that's just the y negative 1. Got to be careful there. The x-intercept, we have to hold off on the x-intercept, and I have it here. See, we set the function equal to 0, but then when we try to solve that function, it turns out that question is, how am I going to solve this function? And we don't know until we talk about the logarithmic functions. So we'll hold off on that one. Now, sometimes we work with base e, and just to kind of show you some things about this base e right in here. Base e here is e is an irrational number, okay, and it's approximately 2.718 non-terminating decimal without repeating blocks of digits, kind of like pi. I have drawing analogy to pi. Pi is also an irrational number, right? So is this one. Again, irrational in a mathematical sense, in that you cannot write these as ratio of two integers. That's what makes the number irrational. Now, e is approximately 2.72, which makes it lie between 2 and 3. So the graph of e to the x is somewhere between the graph of, let's say, 2 to the x and 3 to the x. That's what that is. Okay, but it has that same general shape of all graphs where a is greater than 1. So it's increasing. What does the graph of e to negative x look like? Well, that would be the reflection about the y-axis. See that without plotting points. What does the graph of e to x plus 2 looks like? Well, for this one, if I think of my basic function as e to the x, and if I do f at x minus h, it's going to look like this. And I can recognize now that x plus 2 equals x minus h in this form and in this form. And from that, I get h to be, there you go, negative 2, which means a shift to the left of 2 units. Okay, so I did that. I graphed e to the x, and then I shifted it to the left 2 units, like that. The point, key point, the y-intercept 0, 1 also shifts left 2 units, so that point is now at negative 2, 1. Clearly the y-intercept changes, right? The y-intercept is now, if you want to find it, y-intercept is easy to find. You do f at 0, which is e to 0 plus 2 is e squared. So e squared, remember, e is less than 3, so the y-intercept moved up to about 7 something, 8 something, whatever e squared is. 0 and e squared, that's where the y-intercept is. All right. So we're done with the graph of these exponential functions. Now let's take a look at, we're going to try to solve some exponential equations. Now, an exponential equation is an equation that has exponential functions in it. So we do have this important property of exponential equations right in here. That goes, if two exponential functions are equal to each other with the same base, therefore the exponents must be the same. Bases are the same, exponents must be the same. All right? So let's take a look at an example. Suppose I want to solve this equation. And the equation is 2 to negative x equals 16. Now to get common bases, notice I rewrote 16 as 2 to the 4th power. Once we write it as 2 to the 4th, now they have common base, exponents must be the same. So you set 4 equal to negative x and solve for x. And that will solve it. Very easy if they have common bases. If they don't have common base, then we get into a situation like this. And that's the one we're holding off on until we go through the next section. And we can always check the answers. Usually I don't check my solutions for exponential equations. If I'm comfortable the way I solved it, I feel good about solving it correctly. Because you can check that number and it works. And here I did a quick check, plugged in negative 4 in for x, So double negative on 4 made 4, and 2 to the 4th is 16, and 16 equals 16, so it checks. Again, that's optional. The check is optional. Now let's take a look at this one, which is a little more exotic. For this one, notice bases are not the same. One is 9, the other one 27. So I do need to get a common base here. And because 9 and 27, these are all powers of 3, so I can say the common base is 3 now. 9 would be 3 squared, 27, 3 cubed. And the next step, I'm using the power property of exponents to the right here, this one, to rewrite 3 raised to the 3 to the x power, multiply 3 times x to get this one. And likewise, you do the one before it. Okay, so 2 to the x to the binomial, negative x plus 15, you multiply 2 times the binomial. And then when you do, you simply, because we have the same common base, you equate the exponents and then solve for x. The solving part is easy. You do distributive property, and then you add, once the parentheses is gone, or are gone, you add 2x to both sides, and x turns out to be 6. And then the exponential function, another one. This time I have 3 to x squared minus 7 equal 27 2 to 2x power. Bases must be the same. The natural base here would be 3 because 27 can be written as in powers of 3. And I did. So here's your 27. And then using again the power rule of exponents that we have, we simply multiply the exponents. 3 times 2x makes 6x, and now I can equate those exponents because they have the same base. And equating them, I get x squared minus 7 equals 6x. And here is the equation, the quadratic equation. I moved 6x to the left and then factored it. And by zero factor theorem, we have 2 possible solutions for this one. See how that works? Pretty easy if you have common bases. If you don't have common base, we need to use the method of the next section. In fact, in the next section, we will talk about this. All right, and we are done with this lecture. As always, again, thank you for watching, and I'll hopefully have you in another video. Thank you.